Good morning, children. Welcome to the online webinar classes conducted by Rise Society. Subject, Match 2B. Topic, Parabola, Class 1. Dear children, let us take a brief introduction of what a conic section is. In fact, circle, parabola, ellipse, hyperbola, a pair of straight lines, a straight line, and a point are called as conic sections because each is a section of a double-napped right circular cone with a plane. The plane curves have a very wide range of applications in planetary motion, design of telescopes and antennas, reflectors in flashlights, etc. Dear children, before going to learn about what is a conic section and the different cases when the conic section gives different geometric figures, let us take a glance at the figures shown on the slide. The figure shown on the slide is a cone placed on the other cone vertical in opposite directions. So the upper one is cone 1 and the lower one is cone 2 put together in such a way that vertices join and the axis remains same for both of them. Then the blue colored dotted line is an axis, yellow color point is a vertex, and the angle between the slant line and the blue line which makes the cone while rotating is the vertex angle. The red line is called generator and the angle between generator and the axis of the cone is called vertex angle. And the surface which is in the form of a circle is called directrix. Observe the figure, children. We have generator of the cone and the axis and two curves in a circular path. So it is called axis, the dotted line, and the angle between the generator and the axis is called vertex angle. And if a plane cuts in such a way that alpha is equal to beta, where beta is the angle between the cutting plane and the axis, and alpha is the angle between the generator and the axis of the cone, then the curve obtained will be a parabola. And the plane section of the plane section of the plane and the double-napped cone will be a circle if alpha is equal to, if beta is equal to pi by 2. Let us take the definition, children. Conic sections: circle, ellipse, hyperbola, a pair of straight line and a point are called conic sections because each is a section of a double-napped right circular cone with a plane. Dear children, let us see this definition in detail. This is a double-napped cone, children. I constructed it using GeoGebra file. Now, observe the 2D. We are getting parabola, hyperbola, ellipse, circle. So when plane moves or cuts the double-napped right circular cone in different angles, we get different figures. Observe the figure. Now it is hyperbola. Now this section gives us ellipse, circle, parabola. So all these are the different cases. So this is hyperbola and this is circle, parabola. Hope you all understand. For the different angles that the plane makes with the cone, the plane section gives different figures. So when is the plane section hyperbola, and when is the plane section ellipse, when is it a circle, when is parabola, depends upon the angle made by the plane with the axis of the cone. Let us discuss them in detail, children. I repeat, circle, ellipse, hyperbola, a pair of straight line and a point are called as conic sections because each is a section of a double lapped right circular cone with a plane. Suppose the cutting plane makes an angle beta with the axis of the cone, and suppose the generating angle of the cone is alpha. Then the section is a circle if beta is equal to pi by 2, an ellipse if alpha less than beta less than pi by 2, a parabola if alpha is equal to beta, and a hyperbola if 0 less than or equal to beta less than alpha. Look at the figure, children. This is a cone and plane section gives us a circle when beta equal to pi by 2. And it gives ellipse when alpha less than beta less than pi by 2. And the plane section will be a parabola if alpha equal to beta. And the plane section is hyperbola if 0 less than or equal to beta less than alpha. These are the different cases that we get in plane section, children. Now, what is conic section? The section of double lapped cone and the plane is once again explained all together, children. When is we get parabola, when we get circle, when we get an ellipse, when we get hyperbola. Look at the figure carefully, children. Observe the different angles made by the plane with axis of the cone. It is this angle which makes different plane sections, different curves on plane sections. Hope the introduction is clear, children. So it is the steepness or bend or the angle between the axis of the cone and the plane, which gives us the parabola, circle, ellipse, and hyperbola. The locus of a point moving on a plane such that its distances from a fixed point and a fixed straight line in the plane or in a constant ratio E is called a conic. So to generate a conic, we always need a fixed point and a fixed straight line in such a way that the distance of a points from this fixed point and fixed straight line, the ratio of the distances of a point from this fixed point and this fixed straight line should be constant. Such points form a conic. This is the definition of the conic, children. The locus of a point which is moving on a plane so that it's from a fixed point and fixed straight line in the plane or in a constant ratio E is called a conic. Look at the figure, children. We have a point P such that its distance from S focus and its distance from directrix, that is SP and PM. So both must be equal. So the fixed, that means both the ratio of both distances, that is SP divided by PM, must be constant. Then that locus of P is called a conic. Here, the fixed point is called focus and is usually denoted by S. The fixed straight line is called directrix. In general, it is denoted by L. And the constant ratio E is called eccentricity of the conic. The straight line of the plane passing through the focus and perpendicular to the directrix is called the axis. This line, children, which is passing through the focus and perpendicular to the directrix, is called the axis of the conic. Observe the figure, children. We have two distances from P that are calculated from focus as well as the directrix. If M is the foot of the perpendicular from P onto the directrix, then SP by PM is equal to E is a conic. Therefore, the locus of a point P moving on a plane such that SP by PM, where PM is a perpendicular distance from P to the directrix, is called a conic. I'm repeating the definition again and again, children. If you have this base, then you can do the remaining chapters of the conic section well. If E is equal to 1, then the conic section is called parabola. If E is equal to 1, that means SP by PM is equal to 1. That means SP is equal to PM, then the conic is called parabola. Next case, if eccentricity, the constant value E lies between 0 and 1, then the conic section is called ellipse. If E is greater than 1, then the conic section is called hyperbola. So these are the different cases when we get the different figures depending upon the value of E. Dear children, look at the figure. We have a curve, parabola, in the plane of XY with vertex A. And the fixed straight line is denoted by red color and is L. And S is a focus and P is a point on the parabola. Now we have PM, the perpendicular distance from P onto the directrix. The locus of a point in a plane such that its distance from a fixed point is always equal to its distance from, its distance from a fixed straight line is called parabola. So what is parabola? The distance of the point from fixed straight line and fixed point. This distance, SP and PM, are equal. Then the conic is called parabola. The two distances. What are those two distances? The distance of our point P from the focus, that is the fixed point, and the fixed straight line in the plane must be equal. Then the locus of P is called parabola. I repeat once again. We have a fixed point and we have a fixed straight line. Now collect all those points which are equidistant from this fixed point and the fixed straight line. The locus of such points P is a parabola. That means SP is equal to PM, then P lies on parabola. Now we derive the equation of the parabola in general form. Look at the figure, children. This is a parabola whose focus is S alpha comma beta and is a fixed point. Now we have a directrix and P is a point on the parabola. Now we shall derive the equation of this parabola in general form. Let us alpha comma, this is alpha comma beta, children. Let S alpha comma beta be the focus. To derive equation of any conic, what we need, children? A fixed point on the fixed straight line. Now we have a fixed point as alpha comma beta, and the directrix Lx plus My plus n equal to 0. So we got a fixed straight line and we got a fixed point. Now we shall need a point on the locus. Let Px comma y be a point on the parabola. Then the distance of P from the directrix is Pm, and the distance of P from focus is S. If P lies on parabola, it must satisfy the geometric condition that SP is equal to Pm. What is SP, children? The distance between the focus and point P. So it is x, when square on both sides, x minus alpha whole square plus y minus beta whole square is equal to Pm square, the perpendicular distance of the point to the directrix, which is the square of Pm square, which is Lx plus My plus n whole square by L square plus m square is the equation of the parabola in standard form. It is a second degree equation in x and y. And the equation of axis will be m into x minus alpha minus L into y minus beta equal to 0. Now, we shall derive the equation of a parabola in standard form. Let S be the focus. To derive any conic, we need a fixed point and fixed straight line is clear to all. Let S be the focus and L is equal to 0 be the directrix of the parabola. And let us choose a point P on the parabola. Now, let M be the projection of P on the directrix and Z be the projection of S on the directrix. L is equal to 0. Let N be the projection of P on SZ. Now from P, we have drawn a perpendicular onto the x-axis, also onto the SZ. Then N is the foot of the perpendicular. Let A be the midpoint of SZ. Now we have Z here and S here. S is a focus. Z is a projection of S on the directrix. I just mark it with the red color so that you can get what is focus and what is directrix clearly. This is directrix, children. That is the fixed straight line. And this point S is focus. Now, from focus, we have drawn a perpendicular onto the directrix, and Z is the foot of the perpendicular. Now, from P also, we have drawn a perpendicular onto the directrix, and M is the foot of the perpendicular. Is it clear, children? From P also, we are drawing the foot of the perpendicular. From focus also, we are drawing the foot of the perpendicular. Onto where? Onto the directrix. Now, from P again we are drawing the foot of the perpendicular onto the SZ. Let N be the foot of the perpendicular. And then we have a point A, which is the midpoint of the distances Z and S. So A is a point such that it is ZA is equal to AS. A is the point such that ZA is equal to AS. This is ZA. and the distance ZA will be equal to AS. Okay. So A is such a way that ZA equal to AS. So A is the midpoint of SZ. Is it clear for you all, children? Therefore, SA is equal to AZ. Then A lies on the parabola. Why A lies on the parabola, children? A lies on the parabola because it is following the condition that the distance of A from S is equal to the distance of A from the directrix. AZ is the perpendicular distance of A from the directrix. SA is the distance of A from the focus. Therefore, SA is equal to AZ gives the conclusion A lies on the parabola. Since A lies on the parabola, let us take the distance AS is equal to A. Distance is always greater than 0, therefore small a is greater than 0, children. Now, let YA, Y dash be the straight line through A parallel to the directrix. So this is the line drawn, children, YA, Y dash. Now we are constructing a line. How is this line, children? Is it parallel to directrix? Yes. And we are taking this as our y-axis. And take the straight line ZX as x-axis. And the line YY dash as y-axis. Now let us take ZS. This as x-axis. Okay. The line through A, which is parallel to directrix as y-axis, and the line through A such that it is perpendicular to directrix is as x-axis. Then observe, children, what is A? It is the point of intersection of x-axis and y-axis, isn't it? Then what is A here? A is origin 0, 0. Let S is equal to A, 0. Why S is equal to A, 0? Because we have taken this distance as small a. Then S will be on x-axis at a distance of A units. And S is on the right side of capital A. Therefore, S is equal to A, 0. And Z is also at a distance of A units, but to the left side of the X, to the left side of the origin. And we have concluded that AZ is equal to AS. Therefore, Z will be equal to minus A, 0. Is this clear, children? These are the very, very important things that you need to learn or that you need to focus. Then everything is in the definition. Then the equation of the directrix is x plus A equal to 0. The equation of the directrix. This is the line that I'll take the other color so that you can understand well, children. The directrix I'm marking with blue color. Is it not in the directrix, children? Yes. And is passing through which point? Now our Z is minus A, 0. What is Z, children? Minus A, 0. And this point minus A, through this point minus A, 0, the directrix is passing and the directrix is parallel to y-axis. Therefore, its equation will be x equal to minus A or x plus A equal to 0. Now, we have all the required points Z, A, S, and P. Now, let us take a point on the locus. We have already taken point on the locus. Let P be the coordinate with the coordinates x1, y1, children. And when the point lies on the parabola, and it is a point such that it is satisfying the condition. I'm sorry. We have to take that P be a point. We should not take a point on the parabola now. Let us take that P satisfies the condition SP is equal to PM. Now P satisfies the condition SP is equal to PM. Now we show that P is on the parabola. If that condition is satisfied, please recollect the definition of the locus. If point is on the locus, it should satisfy the geometric condition. If it satisfies the geometric condition, it should be on the locus. Now I am taking P such that it satisfies the geometric condition. What is the geometric condition if P has to be there? Now let us take a point P such that it satisfies the geometric condition SP by PM is equal to 1. Then SP is equal to PM. Squaring on both sides, under root of x minus a whole square plus y minus 0 whole square is equal to x plus a with modulus, children. When we square on both sides, x1 minus a whole square plus y1 minus 0 whole square is equal to x1 plus a whole square. On expanding and on simplification, we shall get x1 square and x1 square gets cancelled. A square gets cancelled. We'll get y square is equal to 2ax plus 2ax. Then y1 square is equal to 4ax1. When P satisfies the geometric condition SP by PM equal to 1, then P lies on the curve y1 square equal to 4ax1. Is this clear, children? When P satisfies the geometric condition SP by PM equal to 1, then P lies on y1 square is equal to 4ax1. Now conversely, if Px1, y1 is a point on the parabola, if Px1, y1 is a point on the parabola, is a point on the parabola. Now, let us see what is SP. SP is the distance between S focus a comma 0 and point x1, y1. So SP is under root of x1 minus a whole square plus y square. On expanding x1 minus a whole square, we shall get x1 square plus a square minus 2ax1. Then what is y? This is y1 square, children. What is y1 square, children? Because P is a point on the parabola whose equation is y square equal to 4ax. Just now we have seen. Then y1 square will automatically be equal to 4ax1. So it is x1 square plus a square minus 2ax1 plus 4ax1. On simplification, it is mod x1 minus a whole square. So it is mod x1 minus, it is mod x1 minus a. Sorry, children. I'm sorry. This is due to the printing mistake. It has happened. There was a problem in the PowerPoint in the last minute. So it is mod x plus a. 4ax1 is plus sign and this is minus 2ax1 gives us plus 2ax1. So it is mod x1 plus a whole square, which gives us mod x1 plus a. So in general, it is mod x plus a. Therefore, the locus of P satisfies the condition SP is equal to PM when P is on parabola. Therefore, what can we conclude, children? We can conclude that if P lies on parabola, it satisfies the condition SP by PM is equal to 1 or SP equal to PM. And when SP is equal to PM, P lies on the parabola y square equal to 4ax. Therefore, we can say that y square equal to 4ax is the standard form of the parabola in this case. Now, let us see the nature of the curve. Let us take a new page, children, where you can understand the nature of the curve well. To construct a parabola, what we always need is a point which is fixed and a straight line. Let us connect these two. Now, let us draw a cone. Sorry, let us draw a parabola with the fixed point. This is the fixed point. So to draw the parabola, we need to tell what is a fixed point, and this is a fixed straight line. Then parabola is given. Is this clear, children? Observe, children. The curve is open both up and down. If you want to move, you can move the curve. First, this curve is extending on upside and in downside. So what can you observe? It's an open curve. Second, observe the length. How many units it is cutting on the either side of x-axis? 1, 2, 3, 4. Similarly, come down. 1, 2, 3, 4 boxes. Like that, if you count the number of the boxes above the x-axis and below the x-axis, it will be equal. That means the graph is extended on the either side of x-axis symmetrically. The curve y square equal to 4ax is symmetric about x-axis. Hope it's clear, children. And now if you take a point on the parabola, 1, 2, 3, 4 units above the x-axis. Similarly, 1, 2, 3, 4 units below the x-axis also, we shall get a point on the parabola. That means for every value of y, we shall get 2 points on the parabola. One is above the x-axis, the other is below the x-axis. So there exist 2 points. Is this clear, children? So this is an example. As you move the focus, the curve changes, but the properties remain same. Now, let us go to the definitions. Nature of the curve y square equal to 4ax. The curve is symmetric with respect to the x-axis. The principal axis is an axis of parabola. What is the principal axis? X-axis. Y equal to 0 implies x is equal to 0. Thus, the curve meets x-axis at only 1 point 0, 0. Hence, the parabola has only one vertex. So, it has only one vertex. What I have shown was the rough diagram. And now, let us take this as vertex. Then how do we get this point? Y square equal to 4ax. In that, if y equal to 0, then x is equal to 0 is a point we obtain here. And this is only one vertex that parabola has. If x is less than 0, then there exists no y belongs to R. Thus, the parabola does not lie in the second and third quadrant. Where it lies only in first and fourth quadrant. The parabola was lying only in the first and fourth quadrants. the parabola does not exist in the second and third. In this case, y square equal to 4ax. In the case of y square equal to 4ax, we are talking about the nature of the curve. Y square is equal to 4ax. First thing is, it is symmetric about x-axis. The second important thing, it has a vertex which is origin. Okay, the vertex is origin. This is directrix. If x is less than 0, then there exists no y belongs to R. So x is always positive. If x is less than 0, then 4ax will be negative. The y square will be a negative value. Square of y cannot be negative, isn't it, children? Square of a number cannot be negative in a real plane. So for all y belongs to R, x is not less than 0. X is not less than 0 in the sense the values are not taken on the negative direction. Therefore, only on positive x the curve is extended in this case. Therefore, the parabola extends only in the first quadrant and fourth, but not in the second and third, children. If x is greater than 0, that means f is positive. Then y square is also greater than 0, and hence y has two real values that we were discussing. Above and below we get two values. Thus the parabola lies in the first and fourth quadrant. So y square equal to 4ax extends only in the first and fourth quadrants. I'm going very slow as per the request of many students that they were keeping personal messages that they did not understand conic section very well when they have gone through the textbook. So please explain the conic section slow rather than not like the circles and system of circles. So considering their request, I'm going very slow. Hope now you can follow the definitions. X is equal to 0 implies y square equal to 0. So y equal to 0, 0. Thus, for single value of x equal to 0, we get two values for y which are 0, 0. Thus, y-axis needs the parabola into coincident points, and hence y-axis stretches the parabola at 0, 0. So, the vertical line touches the parabola only at a single point. Hence, y-axis is a tangent at origin. Now, as we are increasing the value of x towards infinity, larger and larger values, then y square also extends to larger and larger values. It may be plus or minus. So it extends on the positive side as well as negative side. Thus, the curve is not bounded. It is open. That is the reason why we got the curve in open, the right side of y-axis. Definition. Let us take the definitions that are similar as all conics. I'm sorry, let us take the definitions. Curve, focal curve, double ordinate, and lattice rectum. This is a parabola with the directrix L, focus S. Let P be a point on the parabola. Then SP equal to PM. Okay. Now, what is a chord? It's same as chord of a circle, children. The line joining 2 points of a parabola is called chord of a parabola. So, let us take 2 points on the parabola, E and F. Then what is EF, children? EF is a chord of a parabola. It is simply the join of 2 points. Focal chord. If this chord passes through the focus, then it is called focal chord. See, children, this chord is also 2 points, is also joining 2 points on the parabola. But what is the difference between EF and this chord? GH, children, what is the difference between EF and GH? EF is simply join of 2 points of the parabola, where GH is a join of 2 points of the parabola also passes through S. Therefore, EF is a curd, GH is a focal curd. Can you find the difference between EF and GH, children? EF is only curd and GH is a focal curd. Now we shall discuss another important definition, double ordinate. A curd through a point P on the parabola, which is perpendicular to the axis, of the parabola, is called the double ordinate of the point P. We have so many double ordinates. For every point, there exists a double ordinate for every point on the parabola. But what is this? This is a double ordinate, which is perpendicular, occurred through P on the parabola, which is perpendicular to the axis of the parabola, is called double ordinate. Sorry, I could not increase the length here, children. It comes down, isn't it? First, it should be a curd. All these are curds, children. See, this is simple curd. The first definition is a simple curd. This is a curd. Focal curd is also curd. Double ordinate is also curd. Lattice rectum is also curd. What is the difference? Curd is only join of 2 points, like EF. Focal curd is a curd which passes through the focus. Double ordinate is a curd which is perpendicular to the axis, of the parabola. See here, children. Suppose we have pH as a double ordinate. Sorry, pH, if for example, then pH will be perpendicular to axis. This is a criteria needed for the double ordinate. Next, lattice rectum. What is lattice rectum? A double ordinate passing through the focus. See here in blue color, Q and R. QR is perpendicular, as well as it is a curd because it is joining 2 points. It is passing through the focus, so it is a focal curd. And it is a perpendicular to the axis, so it is also a double ordinate. And this is called lattice rectum if it passes through focus. So the double ordinate passing through the focus is called the lattice rectum of the parabola. These are the important definitions, children. Let us discuss these points once again. Let us open the GeoGebra file where we can have the definition, the revision of the definitions once again. Let us take the y-axis. We will pull the graph. Let us take a point through which y-axis is drawn, and this is suppose directrix, and this is the point focus. Let us take a line, children, through these points, which is our directrix. Now we shall draw another line. It will be more thick if I insert this line. This is y-axis. So coordinate axes are represented with the red line, children. Now we shall draw a cone. Sorry, we shall draw a parabola. We shall draw a parabola. To draw a parabola, what we need, children? We need a fixed point and a fixed straight line. So this is a fixed point and this is a fixed straight line. And this is a related parabola whose vertex is at origin. And its equation we know is in the form y square equal to 4ax. Now I shall mark some points, children. Now I will join these 2 points. I'll take a line segment which joins these 2 points. First point and second point. I lost the connection. What is this, children? What is the name of this line now? It's only a chord. It is only the chord. If this chord passes through the focus, then it is called focal curve. We shall take one more point. We shall take 2 points on either sides of parabola and join them. See here, children. This is the chord which is passing through the focus and is perpendicular to the axis of the parabola. Therefore, this is a double ordinate. This is a double ordinate. And this is a lattice rectum. And this is a focal chord. This is a chord. This is first chord because it is passing through the 2 points on the parabola. Second, it is also a focal chord because it is also passing through the focus. And it is also double ordinate. Why it is also double ordinate? Because it is perpendicular to the axis of the parabola. And it is also called lattice rectum because it is passing through the focus and is perpendicular to the directrix. Now, if I take a chord, first we shall remove the previous chord so that you can understand the next ones better. Now, I will reduce the size so that you can understand well. Now I have a line segment. Now this will be the chord and it intersects the parabola somewhere there and is a chord passing through which point? Is a focus. Therefore, this is only the focal chord. This is called only the focal chord. Chord is only join of 2 points and it is passing through the focus, so it is a focal chord. Is this clear, children? The difference between the focal chord and the lattice rectum? The distance between the double ordinate and lattice rectum? Double ordinate is simply a perpendicular line, but not necessarily passing through the focus. See, this is double ordinate. This line is double ordinate. This line is double ordinate, but not lattice rectum because our focus is here. This is perpendicular line to the axis, but not passing through the focus. Therefore, it is called only double ordinate, but not lattice rectum. Now, if I draw a perpendicular, I am repeating again. If I draw another perpendicular line, which is perpendicular to the axis, which is passing through the focus. Now, it is called double ordinate, passing through the focus. Therefore, its name is lattice rectum. So lattice rectum is also a double ordinate. Which double ordinate? The double ordinate passing through the focus. Like curve passing through the center of the circle is called radius. So double ordinate passing through the focus is called lattice rectum. So with this, we have finished today's introductory class, children. Thank you all and have a happy reading, children. And stay home, stay safe.